So Ted already gave a bit of an intro, but just as a further recap. So in the previous chapters, we've learned about various different things, but we've kind of been operating under the assumption that things are going to work. And then as we scale to more and more systems, we know that eventually things are not going to work. Networking is going to fail, systems are going to fail, other kinds of things are going to go wrong. And so in this chapter, we're looking at the pessimistic side of things. So assuming that your code is correct, there's still things that are going to potentially cause problems. And so we're looking at the whole system and just basically saying, what could go wrong? Assume it's going to go wrong. How are we going to handle that? And so when we work with more and more systems, there's more likelihood of failure. And so if you have potentially 1,000 systems, it's almost guaranteed that at least one of them is going to be disconnected or fail in some way. And so the first section, we're looking at faults and partial faults. And so when you do this with a normal single system application, so you just have your one application, it's running your Google Chrome or whatever, if it fails, you expect it to just completely fail. But when you're doing something with distributed systems, it can fail and it can be a bit more gray because many different systems can still be operating normally, but then only a subset of them might be operating incorrectly potentially. And so that can manifest in a lot of different ways. And so there can be individual system failure even in a distributed system. So say you have 1,000 systems and one of them fails, that might not be that big of a deal. But if you have 1,000 systems and the entire an entire data center goes offline or something, that might be an even more significant problem because an entire region all of a sudden has extremely high latency or something like that. And then one of the parts with that is when you have partial failure, it's not always obvious exactly which part is failing. So you might have one system that is able to receive a request, but it's not able to return a response because it's improperly networked or something like that. And so later in the chapter, we'll look more at kind of determining the failures and understanding what can go wrong there. The next section, they were looking at cloud computing versus supercomputing, and they were kind of saying supercomputers is a very well networked, very well integrated single system, basically. It might actually be physically multiple systems, but they kind of operate as if they were one system because they're very tightly coupled. And so typically with a supercomputer, what people would do is they run some sort of work and then they just checkpoint it periodically. And then if something fails, just a single system out of the whole supercompute cluster, then they just pause things, fix the system, and then get it back online, and then continue from that checkpoint. But that's not really possible with cloud computing, because if you're saying I have 1,000 systems, they're distributed all across the world, you can't pause all of US operations because some system in South America failed and you need to get that back offline or online. And so one of the things I was mentioning earlier is as you add more and more systems to a cloud compute network, eventually you are basically guaranteed a failure. As you grow more and more, it's more likely that more things are broken, but you also have the benefit of you have other systems to fall back on potentially. And so you have to assume there's at least some failure at all time, and you have to build some sort of tolerance inside of the application. So one of the things that can happen is a system can just directly die. A hard drive dies, memory dies, something goes wrong with the processor, the power supply dies. But then there's also the problem of just unreliable networking. So you might have a system that is actually responsive, but it's just disconnected to the network. And so in this way, we can't necessarily always have the systems just like fully interconnected. It's not like they're sharing a whole lot. And so we have to build with this assumption of shared nothing, that they can operate as their own atomic units, basically. One of the things they were noting is that most networks are asynchronous packet networks, and that there's no real guarantee on the transmission, either in terms of the message will actually get there, and also in terms of when it will actually get there. It can take varying amounts of time for it to be received and sent and stuff like that. So there's a whole bunch of different scenarios that can go wrong there. A request might just get lost. Request might be delayed because of other traffic. There's just congestion and it slows it down a bit. The receiver of the request might have died, so you might have sent it and it got there correctly, but then the system isn't actually there to receive it. It might be that the receiver is just temporarily unresponsive. There's various different conditions where it's just not available at the time, but it might be back later. It could be that the request got sent, it got received on the other end, and then the system sent a response, but the response didn't actually arrive back at the system. And then you can also have the case of you sent the request is received, the response is sent, and then it's just delayed. It's not necessarily that it's lost, but it just comes back very late. And then in all of those different scenarios, it's basically impossible to tell exactly why no response might have been received. It might just be that it's still in the pipeline and it's going to arrive a few milliseconds later. So you can't necessarily say the information was fully lost until you have some form of confirmation. And so they started posing this idea of some form of a timeout. So beyond a certain amount of time, you can say, okay, this information was actually lost. But before that time, we're just going to basically wait and just say, I hope that this arrives. And then if it goes beyond that point, then you say, okay, something went wrong. Let's either retry or announce that known dead or do something else there. And then they started talking about the network faults in practice. So the actual hardware itself has gotten more and more reliable, but there's still the potential for human error. So someone misconfigures something, someone accidentally shears a cable, or the data center gets run into. There's all kinds of different things that can happen there. So there's no 100% guarantee of anything. If a cable gets unplugged, a cable gets unplugged. There's no way to make sure that the packet still gets there necessarily. And so in some applications, it's actually fine to just say, okay, we lost networking for a little bit. Here's an error, try again in 5 seconds or something like that. In other scenarios, it's not necessarily possible to do that. So just to be conscious that there's the possibility to not be completely fault tolerant, but your application still works okay. It's not necessarily a requirement to always be completely fault tolerant, and it's actually probably too expensive in most cases to be tolerant to every single failure. Any questions up to that point? Anything anyone wants to discuss?
I have the following questions. I've heard that supercomputers are way too expensive than distributed system. Was it covered? Did the author said anything about it?
They didn't really talk very much about the cost necessarily.
Okay. And
Yeah,
another thing, okay.
I was just saying, yeah, but I mean, you can't run Facebook on a supercomputer, so it's it's kind of the author didn't say so, but yes, basically they agreed with you.
And about pessimistic and optimistic things, it is like with glass half full. From other side, yes, it is something usually is breaking, but from another side, from another hand, something is up and working.
Mm-hmm. Yeah.
Yeah, I think what you'll see as you get towards later in this chapter and then eventually the next chapter is if you can sort of enumerate all the bad things that can happen, then you can model how you would actually deal with those, right? How you could provide some level of guarantee in the face of those types of situations. And ultimately what we'll see is that unfortunately it's not perfect guarantees that are really cheap. But nevertheless, you can provide certain kinds of guarantees that unless this type of situation happens, then we're good. So that's the purpose of this pessimistic exercise, is to really enumerate what can go wrong so that then we can devise algorithms, or we can devise strategies to say what's, in these minor faults, what can we do? In this major fault, what can we do? And at some point you're going to say, and in this type of disaster, we actually won't be able to handle it. It'll actually cause corruption or something.
Yeah. So I mean, on the one hand, with the distributed systems, it's true that some things are down and some things are up, and it's good that some things are still up rather than the whole thing being down. But it's also possible, if you don't write things in the correct way, that one thing down brings all of the things down. So you have to build the application with that in mind, potentially. So it just adds some complexity, potentially. So moving on to detecting faults, one of the things is you have that sort of uncertainty of, you send a response, you wait for a reply, and then you don't get anything potentially past that timeout limit. You need to be able to determine, is that system actually down, or is it just delayed, or is something else going on? And so that can be a kind of tricky process, but you need to figure that out, because in that imaginary scenario where you have 1,000 different systems, if you have systems that are just going down over time and you're not realizing it, let's say you've got 100 different systems that's going down, your load balancer is sending out requests to all of these different systems. It's wasting time sending it to 10 different, to potentially 100 different systems that are all going to maximum timeout and then going back. And then it's just basically random chance that it's going to eventually land on a properly functioning system. So actually removing them from the network makes everything faster, because you're not just waiting on a bunch of retries on bad systems. So it can be extremely powerful to actually just detect something and remove it from the system entirely. And so previously we've talked about the sort of single leader systems with the databases. And so in that scenario, you need to be able to assign a new one. And that's another way of kind of detecting a fault. You need to know that the other leader went down in order to find that you need to assign a new one, basically. So there's various different conditions. If a system is down, but the application is still up, it's possible for you to receive useful information saying, okay, the system is still alive, but for some reason the application crashed. So this system is there, but don't use it anymore. And so if the operating system is still actually operational, then it can actually return information and say, I'm down right now. So it cuts out that whole uncertainty of, is this system available or not? It can directly announce and say, I'm no longer available. I'm not running the application correctly. And that can save you a bit of time. One of the other things is, depending on your setup, it's possible to use some sort of management tools to directly query the systems and say, are these up? And you can say, okay, this is unreachable on the network, so I know that I can remove this. Then they were talking about determining timeouts and unbounded delays. And so it's pretty difficult to determine the correct amount of timeout. It's not some general rule. You can't just say, okay, if it takes longer than 5 seconds, then mark it as timed out, because it just depends on your network setup and how intensive your operations are. So you might have a system that's all the way across the world, and you just know that there's a certain amount of network latency. And then on top of that, you know that it's doing some intensive operation. So it might just take an extra 5 seconds to respond just because it's busy doing something else. And so depending on your workload, depending on your network configuration, depending on a lot of different things, you have to decide what an appropriate timeout time is. And so there's different trade-offs. If you set a really low timeout time, then you might prematurely assign systems as dead, and you don't really want that, because then you're taking systems out of your workforce that are perfectly well capable. They just might be slightly slower than usual. They just have a single bad request and then they get kicked off. But at the same time, you don't want an excessively long timeout, because if you're doing something and a user makes a request and you've got a 30-second timeout, they make a request, they have to wait 30 seconds for it to even raise an error or something like that. And there's various different other downfalls there. And so one of the complexities is we have unbounded delays. There's no guarantee on when stuff will be delivered, just inherently based on the network and based on the way requests and stuff are handled. If they have multiple things queued up, then they have to take them as they come, basically, and the ordering and the timeliness of things isn't really guaranteed. So you can run into the case that multiple systems are sending information to a single system. So they in the book, they had a diagram of 4 different systems all sending stuff to one single system, and then, sorry, getting a call. And so they have multiple systems all sending to one system, and then if it has to do 4 different things at once, one of them or 3 of them are all going to have to wait on the previous ones to be completed. You can also have this scenario that the system is just busy, so it's just doing some intense computation, and then it can't actually address the information that's been sent to it yet, so it has to just wait a little bit. And then they also pose the scenario of you might have some virtual machines that's just busy doing something else, and just in essence, it looks like it's frozen for a little bit. They also mentioned that it's possible to have a noisy neighbor. So if you're operating in some data center, you're using EC2 or some other AWS type thing, you might just end up on a server that's next to another one that is doing a lot of intense intense operations, and that kind of slows you down in some way. And so they recommend that you just kind of find this out experimentally. Any questions, comments up to that point?
How do we peel off the network outage or delay, the effect of that from the hardware or software performance?
How do we peel it off? Is that what you said?
Yeah, peel off the a network delay or outage.
I don't know that it's really possible to eliminate the delay or outage. You can definitely have better configured networking and redundant connections and stuff like that. But I think that it's something that you kind of just have to expect to happen and build the application accordingly. You can't necessarily 100% eliminate it. With latency, it's just guaranteed that there's going to be some. It's just the physical limits of things. But then the outages, there's just too many things that can go wrong. I've heard plenty of data center stories where it's just like some construction worker hit a water main and it just takes out a whole data center, or they directly hose through their main fiber optic line and stuff like that. And it's you'd hope you could defend against everything, but it's just the reality of the world that stuff happens.
Yeah, I think normally you don't do that. It's the IT people with the, for example, load balancer that automatically detects the outage server and take it off.
It's especially in a distributed system, one of those things is, or one of the things that really comes up is everything has to be done from the perspective of the agent that is doing it. So if I need to make a call over to that server over there to do something, then from my perspective, if it doesn't come back, then I'm unhappy. It really doesn't matter where that came from. Like, was it a network link that failed? Was it, router misconfiguration? Was it a server that was overloaded? Was it like all of these things happen? Like once I send my request out and I, don't get a response back, anything could be it. And that's kind of so from a first pass, if you're just wanting the system to kind of move autonomously along, you have to kind of build the system from that, as you know, Ryan's been saying. Separately from that, I wait for one of my headsets to go. Separately from that, you have the case, like if you're actually trying to troubleshoot and solve some of these items, it becomes situational, right? And you have to start collecting a lot more information from a lot of the different places to be able to do that, right? So it's like, oh, how do I know that my network link is out? Or how do I know it's the server being slow responsive? And it's like, there's all these different symptoms that can come back that may or may not, like, and they all these symptoms mask other symptoms. So it's like, okay, the debugging of it is a extensive and broad item that comes up in situ.
Sorry, I have a quick stupid question. Somebody mentioned load server a minute ago.
Load balancer.
Load balancer.
Oh, load balancer. All right, stupid question. Can a load balancer, is it distributed?
No. Well, yes. There are different types of load balancers, I think is kind of the thing. There are some where it's like you can technically DNS as a load balancer, depending on what your definition of a load balancer is. DNS is distributed, and you can do geo routing with regards to DNS. The IP routing itself can be a load balancer. But then you also have devices and software that people think of as load balancers, which tend to have a little bit of high availability characteristics. Like you'll have a pair of them working, or you'll have like a cluster of them working together, but you don't really see those distributed across the planet. There are some models of that, but your majority are, you know, much smaller.
Yeah, I can second to that one. So you have different level of load balancer. One probably just located in your intranet, and you also, if you have a distributed system around the world, you have the global level load balancer.
That's so typically a CDN.
So how I would sort of summarize that is that no matter what your strategy is, it's ultimately going to start with a single thing. So for example, if you just type in your browser facebook.com, right? Everyone's typing facebook.com, they're typing the exact same URL. So at some point, it has to just be a single thing. But like Chris was saying, it could be that a DNS at that point actually directs you to different physical IP addresses. And then behind the scenes in a data center, one physical IP address, you could actually distribute that load over multiple physical boxes and things like that. So ultimately, if your question is, do people ever have like multiple servers partitioned responding to load? Yes, but it does take strategies, because the whole point of load balancer is that you're hiding that from the end user. The end user just gets to type facebook.com, and they don't have to think about, do I want Facebook 1, Facebook 2, Facebook 3? You know, unlike, for example, some places you go and you say, oh, you can download this from one of our 20 mirrors, and you have to manually pick which of the mirrors you want.
I think y'all are talking more about load balancers for web serving, but I think the question might be more about, you know, serving machine learning models, dynamic pages, because CDNs handle most of that in caching. There's a lot of layers of caching and CDN happening for static HTML. But when you or even, you know, JavaScript included, but when you get to the point of having a service that your company is providing that required to run on a machine, the service itself is distributed, but the load balancer is not. So the load balancer is just a node on your network that decides which server does the work.
Thank you for clarifying. That's great.
Yeah, and I'm not sure, Hobbs. I mean, I think it's probably super rare, because the work of a load balancer is so light that it can handle a massive number of requests. But I think there are technologies that if you really needed to, you can even have multiple load balancers.
I was just thinking of what this question was about. I mean, like, should I create a load balancer? Is what I heard. You know, okay. Should my load balancer be distributed? And the answer depends, as you pointed out.
So Ted, what do you say the load balancer, the workload is so light that you only need one for it? Because if there's like everyone is typing on Facebook and then they all routed to the same load balancer, shouldn't that be really high traffic?
What I meant by that comment, and if other people have more expertise, please help shed light on this. I was simply saying that the work of simply saying, oh, you want a web page from Facebook, go here. That sending the work go here is a lot smaller than say the work of actually serving up a web page.
Yeah, and that
so that's why I'm saying
that's the DNS.
Heavier workload.
Yeah.
The first step is hitting the DNS to get the IP address. Then based on that IP address, you route to the real server or maybe another.
Right, but I'm saying like, for example, if you're hitting an API, you can actually spread that the physical boxes that are serving that request over multiple machines, and so the act of redirecting the API to another box is generally a lot less workload than serving the API itself.
It's so light that you can have a little Raspberry Pi doing it for a whole corporation. It's a router. That's all it is a router. It's just choosing an IP address. And so it doesn't have to do any computation. None of the bandwidth passes through it. It's just returning a few bytes of information to the client.
There's a lot of things that are inline load balancers. So the bandwidth.
Quick question about routers, because I've always had this question. Those routers, the rate at which I don't know, is that part of the standard? The rate at which it, you know what I mean? The bit stream that comes in, can it go faster than a certain hardware frequency? I
want to draw a quick line here from the standpoint of there are things that part of the problem is that we say load balancer and what we mean is kind of load balancing techniques, and in some cases what we mean is actual devices that are doing, say, layer 7 load balancing or layer 3, layer 4 load balancing. And so we can all be saying the same correct thing, but it's really based on the context that we're talking about. So the last question I think was more along the lines of, it sounded like it was a router kind of base, or a router or switch based item. And what you'll see is that when you plug into, either on the wireless or you plug into a switch port, you'll be told, hey, you get 100 megs of traffic, or, a gig of traffic, or 240 megs of traffic, depending on what your connection is, right? And then it's a matter of how fast can that device, move that traffic across. And it very much depends on the model. Some of them are oversubscribed from the standpoint of they say they can do 10 times as much, as long as not everyone is doing their full allotment at the same time. Yeah, they can totally process it. And then there's other devices that are like, yeah, we're listed as line speed, which means if every connection on this device was running full speed with regards to its, uniform packet flow, which is a different issue, then we guarantee all these levels of, what we say, when you get a gig port, you get a gig traffic, right? So it for that case, yes and no, or I mean, it depends on the device.
Yeah. So Sanke, are you talking about like the network level, like an Ethernet router?
Yeah, basically, I heard someone, or was it Chris, mentioned 100 megapips, whatever. Yeah. When it comes to balance, you can't go. That's a hard limit. How you can't go.
Yeah. So there was a time when Ethernet, for example, they had shared media. Okay, so like coaxial Ethernet, you had multiple devices all talking on one medium. We've pretty much evolved past that. So they're now switched networks where everything's point to point with a dedicated line. Okay, you don't have shared medium. And so what Chris was talking about is, let's say you have a router and it has 20 connections. Okay, If you're using 100 megabit Ethernet, then that point-to-point connection is limited at 100 megabits each direction. If you're using gigabit, it's limited to 1,000 megabits, each direction. Okay, but the way those switched routers work today is they're basically just a computer where they get a signal, they read it, they say where's the destination, and they forward it. Okay, so because it's no longer shared media, because it's all point-to-point, in theory, if you have 20 connections, you could have computer 1 talking to computer 2, computer 3 talking to computer 4, 5 talking to 6, and there's no crosstalk. They're not competing to talk to the same computer, right? If your router's fast enough, in theory, if it's got 20 connections, it could be serving 10 gigabits simultaneously because they're all just, separate conversations, each operating at the full gigabit, right? And so what Chris is saying is, depending on how expensive your router is, it may be fast enough to do only 1 gigabit total of packets that it reads it and forwards it somewhere else, reads it, forwards it somewhere else. Most of them are going to be able to do 2, 3, 4 times that or whatever. If you just go to, Walmart and buy yourself, a 20-port router, it's probably not going to be able to do 10 gigabits, where it could just do full bandwidth on 10 simultaneous parallel conversations. It's just going to max out at a certain speed, because at the end of the day, it's just a little mini computer in there that reads the packet and then forwards, it creates a new one. There's no circuit technology where the data actually literally flows through. It has to just read it, consume the message, and then on a new point-to-point, it says, oh, you want to talk to computer 7? I'm going to now create a brand new packet on computer 7 for you. Does that make sense?
Thank you, Ted, for elaborating. Thank you, Chris, for mentioning level 3, level 7. I didn't mean to go on a big tangent, but thank you.
No, it's great.
And
questions are
I will
always
say, manufacturers are never going to give you more than what they guarantee. There's a little bit of, empirical, you might get like 1% or 2 kind of thing. But they'll never give you more than they guarantee. It'll always be less. And that is not necessarily what the theoretical or the information theoretical max of what that technology, what that frequency is doing. Like there's always going to be some that value will always be higher, but you're never going to see that, and you'll never really see more than what the manufacturer tells you. Which is why a lot of them won't actually give you straight answers on some stuff.
I was kind of wondering about the same thing, because I've done transfers between, say, one system to another, and I've said, wow, I get really good speed, but I've never known, am I sharing that tube with everyone else in my family, and I'm eating up the full gigabit per second at the time? And I've assumed not, but I wasn't sure about that. And I think also the mechanisms of that kind of change, because typically we're connected wirelessly too. And I think that in some way might be a more limited pipe. You can't just
sorry, I was going to say, wireless does go back to what Ted was talking about, the hub networks versus the switch networks. But that being said, a lot of wireless networks have the multiple antennas. So you get the multi-input, multi-output. And so it can kind of do this it can do this, it looks a little bit more like you get a dedicated, connection to you. So even that is kind of gone a little weird, but
yeah, I don't know the details. I don't know if anybody knows, but it used to be Wi-Fi. It was just sort of like, here's a frequency and people have to take turns talking. But the protocols have evolved more now, where you sort of ask for a reservation of bandwidth and you kind of get it. And then you go full speed talking, as fast as the bandwidth allows. And then periodically people, request bandwidth, and you have to ultimately maybe give some up to share it with, your brother who's downloading something in the other room. Yeah. But it's not just sort of this wide open bus thing where people have to sort of I think there's sort of a host that's sort of apportioning the bandwidth, right?
Yeah, air traffic controller. Yeah, so they do a little bit of air traffic control with that, but and at any given time, at any given time, one frequency can only really carry one wave across it, right? because anything else causes interference. So that's what they're still trying to work through. But as I said, with the multiple antennas and the multiple connections, you can actually, you don't necessarily hit on the same frequency. You actually spread that out a little bit, so you get more overall bandwidth. But that means anytime stuff's going, someone has to be like, oh yeah, you get this much and you get that much and you get that much. And that's what a lot of the access points are doing nowadays, is they're really just doing air traffic control.
The other thing that I've kind of wondered about is, so I've this is just a general network question. In the past, I've had something like Ted was talking about, where like I myself am downloading a game, but I'm also trying to be in a call with someone, and so I'm also uploading some signal, and I've had issues with the upload. So I'm assuming that whatever the wireless speed, it has to be split between the download and the upload. So I only have a fixed amount of bandwidth for both. Basically, I can only transmit and receive a split amount of that signal, basically. Does that potentially change when I am directly connected, like hardwired? Does that mean that I then have 100 megabits up and 100 megabits down? Or is that the same problem?
Yeah,
I'm splitting a 100 pipe between two tasks.
So there, from the standpoint of the lines, it's really what your line carrying capacity is. So when you're plugged in, you're going over, depending on which spec you're on, like 2 or 4 network cables. Inside of the network cable you plug in on, there's a bunch of smaller cables that actually carry the connection. And so they have something called, half duplex and full duplex, which basically says, full duplex says I can send and receive at the same time. Half duplex means you're only sending or receiving. You're effectively using one of those cables, not, a send cable and a receive cable. And so that's what you see with a lot of the wired stuff. The wireless, again, it comes back to the technology. And again, and now that we have multiple antennas and multiple frequencies that can happen at the same time, you can create a full duplex setup. But again, at any given time on one frequency, you're going to be bound to only sending or receiving. So it really depends on the technology. And yeah.
I think another part to your answer, Ryan, is that as far as I know, everything uses sort of the TCP model for communication. Okay. And so in the TCP model, everything that you're doing is independent and oblivious to everything else that you're doing. So even though it's all coming from your computer, those different apps, like if one's doing a download on your browser and one's doing, whatever, a Zoom chat, they don't coordinate what they're doing. They just each independently do what they do and try to use as much bandwidth as they can. So what happens is, wherever your bottleneck is, anytime you go from more bandwidth to less bandwidth, okay, so it could be just your computer can generate packets a lot faster than your network can accept them, whether it's wireless or wired, right? Or it could be that you've got this wonderful gigabit within your house, but then you get to your cable modem and it's way less, right? So at that point, what's going to happen is things are going to queue up, and eventually, if that queue overflows, packets are just going to get dropped. And so the way TCP works, it's pretty miraculous, is that the only feedback it gets is how long it takes to get replies and whether any of them time out. And so the design fundamentally of TCP is that applications will start with a certain amount of bandwidth, and if it seems like they're getting all of it, they will gradually ask for more and more and grow to fill the pipe. But as soon as they need to share it, generally what happens is the queue overflows and packets get dropped, and the packet drop is telling TCP, whoa, it looks like we've overflowed, now we need to throttle back on how fast we're sending stuff. And so TCP will do this constant business of throttling back and then trying to gradually increase to see if it can use more without overflowing the pipe. So anyway, so that's how that works. And so basically, if you've got a download going and it's using up all of your bandwidth, if you then try and start a Zoom at first, at the very beginning, what's going to happen is it's going to drop packets because there's not enough bandwidth. And then eventually the two will settle into an equilibrium where they're sharing the bandwidth.
Interesting. Cool. Getting back to the book, we've talked a decent amount about networking at this point now, but they were kind of pointing out the example of a phone line, which operates, it has a circuit that's formed and then it just has constant communication. And so under that assumption where it's only doing the one constant stream of bandwidth, it's able to put a bound on the amount of latency, but also on the amount of bandwidth, but it has no flexibility. It's only able to do a single stream task, basically. It would be nice to have those same guarantees to be able to say, okay, it's always going to be 8 milliseconds between these two lines, but it's not necessarily possible with the way things are set up because the workloads are much more bursty and you need more flexibility in what you're able to send. And so they also mentioned, this is kind of in line with some of the stuff we were talking about, the quality of service and admission control. If you ever go on your router at home, you can fiddle with some parameters and you can rate limit people and set various different things on quality of service. And you can say, okay, you can't, this system can't use more than 5 megabits because all it's ever used for is Netflix. And whenever we use it, it ends up pulling too much bandwidth from everyone else. So you can do various things along those lines. Moving on to the clocks section. I originally didn't think clocks were that interesting, but reading through all of this, I thought it was actually kind of fascinating how inaccurate everything is, and how important a lot of things are on it. So they were saying timing's really important for all of these different things. You can, checking if a request is timed out, you have to make sure that the time is actually accurate. You might have something where, like, if your time just gets resynced after you just send a request, you can actually say that you received a response hours later when in reality it was milliseconds, or you can say that you got a response before it was even sent, or something crazy like that. And you probably want to capture your, in previous chapters, we've talked about 99th percentile response times and stuff like that. So you want to see how fast things are typically responding and what's the slowest. And if you're measuring something like that, you might have something that's saying that your 99th percentile response time is 20 seconds, when in reality that was just caused by a time sink or something like that, throwing off your numbers. And then you might have something where you want to know how many queries have happened in the last 5 minutes. And if your definition of what the last 5 minutes was changes, then that might actually change the amount of queries that you're seeing. And they list off a few other things too. They're saying sometimes all that really matters is the duration of things. So you're saying it took 5 things for this thing to happen, or it was 5 seconds since this other thing happened. But then other times it matters the absolute point in time. So like us starting today's meeting at Saturday at 12, it's more important that we agree what Saturday at 12 is more than it is that we met exactly X hours from the last meeting necessarily. They were saying that it's pretty tricky because when you have many different systems, you have to get some form of agreement within a certain bound. And so within each computer, there's a quartz crystal oscillator that kind of keeps track of the time, but it's not really super accurate. So it can get you in the right ballpark, and it can operate even if you go offline, it will keep trucking along and keep you in the right zone generally. But they were saying that you can drift as much as 17 seconds in a day. And so across significant periods of time, you can end up minutes or hours or days off if you let it keep running. And so there's this protocol, network time protocol, that essentially syncs with some sort of authority and then uses that time. And so it gets everyone on the same page. They have some server that uses more accurate methods and then says, okay, this is actually what the time is. And then everyone sets to that. So if you go to your computer on Windows or wherever and you say automatically set time, it's probably making a request to those servers and then saying, okay, this is the true time. Whatever you had before, just throw that away, just align it with this. Then they were talking about the monotonic versus the time of day clocks. So the time of day is the sort of global time. It's saying it's this day and this time and this minute. And then a monotonic clock is saying basically it's been this many units since the last thing applied. And so the monotonic is better for the durations. It's still not necessarily perfect, but it's better at saying with 100% certainty, I know that this thing happened after this thing. Whereas the time of day, because it's being synced with that NTP, you might say, okay, I made this request and then time synced, and then now I'm saying that I received the request 5 seconds before I sent the request. And so things can end up awry there. They were talking about the clock synchronization and accuracy. I already mentioned the quartz crystals can end up drifting over time. And then with sufficient drift, you might end up running into problems with not being able to interact with other systems, not being able to do various different things because it's just so far gone that it doesn't line up. They were mentioning that the NDP synchronization is only as good as the network delay. So if you make a request to the NTP server and you say, what time is it? And that took 50 milliseconds, and then it returns a response back, and it took a certain amount of time for it to process a request and then send a response, say it's another 10 milliseconds or something imaginary, and then it takes another 50 milliseconds for you to receive that request. That means that whatever time it was when you actually sent the request has changed. The time that the NTP server had when it sent you the request has changed as well. So there's still going to be some amount of delay no matter what you do. You just can't get over the physics of the problem. They were mentioning that it probably generally doesn't happen, but if we're preparing for all kinds of scenarios, it's possible that the NTP server is wrong. It might have been misconfigured. It might be operating on some different assumptions where it might just be erroring in some way. And so you can end up desynced because the NTP server itself is wrong, and then that can cause all kinds of issues for your own application. They were saying virtual machines, kind of mentioned this earlier, might be busy doing something else. Some other virtual machine on the same physical hardware might be doing something, and then it kind of snaps back to whatever the other task is, and then all of a sudden it jumps forward in time, and that can cause problems. And then it's even possible for people to intentionally change things. So for any of you who have played Animal Crossing or various different mobile games that might have some form of a timer in it, you might intentionally change the clock and do some time traveling in order to unlock certain things in a game or something like that that require actual in-game time stuff to happen. And so if you have an application where you think maybe my user is going to intentionally change something, you might have to build something in to plan for that. Then they talked about how we're reliant on these clocks to be synchronized. So we've kind of talked about the various different ways that they can get desynchronized, but actually looking at it, it can cause lots of very significant problems, even with small discrepancies. One of the big issues is that it's hard to tell when something's actually been desynchronized because it's typically not a problem up until it is. So you can have something drift in time and it doesn't really matter. And then all of a sudden you end up in some weird scenario where it overwrites some important data, or it gets so far misconfigured that it can no longer interact with the rest of the systems, or any number of different things. So one of the scenarios they were laying out is if you want to keep track of the order of some events from multiple different systems, they all send their request and they say when they sent the request. So for example, they say, I want to write some data to a database. and there's two different systems. One of them does it first, the other one does it second. But because their timing is different, the one that does it first might show up second, and then it might overwrite the second, more recent write, and you might end up in scenarios where that goes awry. So they mentioned that you can try to make timekeeping as accurate as possible, but in some way there's going to be slight discrepancies. You can't necessarily make all systems exactly perfect. So you kind of just have to plan for that. One of the things they mentioned was some Google service where their clock readings have a confidence interval. So they know that it's between this time and that time. And then they look at their two requests and they say, okay, this one is confidently in front of the other one because it doesn't overlap in any way. But then if they see that there is some potential overlap, then they might handle it in a slightly different way and say, okay, we think this one is after, but it also has the possibility of being before. And so they were also talking about backup. So in previous chapters, we've talked about you might eventually want to take a database backup and you just say, okay, this database is just being constantly written to. So eventually I'm going to have to take a snapshot. So I just say everything before this set time, I'm going to write that down and store that off as a backup or put it somewhere else for analytic purposes. But if you don't agree on what the actual time is, if you say, I want everything before this time, but then some write occurred after that, but under your timekeeping, it happened before, you might make a backup where you just lose some information. And depending on your scenario, that might not be an option. You need something that's actually correctly lined up. Then they talked about process pauses. So they had these diagrams with leases. And so they're saying, like in the single leader model that we talked about in the past, the leader might say, okay, I'm requesting the lease to be leader. And periodically it has to go and renew that and say, okay, I'm still alive, I'm still the leader, everyone follow me still. But they laid out this scenario where maybe it pauses for it a little bit, maybe it loses network connection, maybe it's busy doing some processing, maybe it doesn't have the capability at a certain time to renew the lease. And in that time, another system takes over as leader, but then it unpauses and it still thinks it's the leader, and then it makes some write in the meantime, and then it goes to actually renew the lease, and then it says, oh, now I'm not the leader, but I already did this problematic write, and I've got information that the other databases don't have now. So they laid out that scenario, and then later we'll talk about some way to try to prevent that potentially. They laid out that it's possible to get some sort of real-time guarantees. You can use a real-time operating system. You can constrain yourself to certain different programming languages, and you can try to do that in various different ways. And I know that some systems, like all of the autonomous vehicle software, has been pushing in that direction because you have high constraints for you can't have your system just pause for a second or 50 milliseconds or anything like that. Anytime something happens, it has to be able to respond immediately. But it's extremely expensive because you have to write things in an entirely different way in different programming languages on different operating systems. So for most use cases, it's not really worth it to do that. One of the things that got mentioned multiple times, garbage collection calls can cause significant pauses depending on exactly what the system setup looks like. So you have to be kind of wary of those. It might not even be that something is going wrong. It might not be that the system is disconnected or some other hardware failure or something. It might just be doing garbage collection, and then you have to be aware that it's doing other work and isn't immediately available. Then they had a sort of philosophical section talking about knowledge, truth, and lies. And they're saying that it's kind of difficult to determine what is reality. So if you have your system and it can't see another system, do you assume that the other system is just gone forever? Is it coming back? Did it even exist in the first place? There's all kinds of different philosophical things that you can go through, and it's kind of the same in real life when you're saying, okay, does my phone actually exist? Well, because I can perceive it, I'm going to say that it exists. But there's a lot of different mental gymnastics things you can do there.
I do want to highlight something here real fast. Is a lot of the stuff where we make, to the point about stuff not being, or the senses being faulty. We run into it all the time where it's like someone says the network is down or this is failing, right? And you can kind of drill into stuff and be like, oh, okay, the service they're trying to access is having a problem or whatever. Or even their own service, going back to say the garbage collection, right? It's like, oh, I tried to access this thing and my browser, and browser's a bad example, but my browser, didn't have, it didn't respond to me. It's like, well, the browser was doing garbage collection. So it's not that the website was down, it's that your own system and your use of measurement was giving you a false sense. And it crops up all the time. And we continually trip over stuff where it's really what is the perception of reality.
Mm-hmm. Yeah. We have that even on just Zoom calls and stuff. Someone starts lagging out and everyone goes, is it them or is it me? And then you have to figure out, is everyone else occurring on this problem or is it just on your end? There's lots of different ways that can manifest.
Which goes to the next section.
Yeah.
Defined by the majority. Yeah.
Any other comments, questions before we move on?
Just a random share. When I was in grad school, I had this friend Arvind, and he was, whatever reason, there was this thing that we would just chit chat and joke about, which is like, how exactly does the operating system handle like scheduled jobs when you have all this weird time stuff, right? So there was no easy way to test the scenario where like you have a job that's daily at midnight, but like you said, Ryan, like let's say like the clock could be off by 17 seconds, right? So what if at 5 seconds before midnight it, asked for the correct time and it advanced 17 seconds and it just skipped to 12 seconds after midnight, right? But so the thing that he wanted to do was a slightly different version, so which is daylight savings. So I can't remember exactly how it works, but I think like when you fall back, it goes from 2 a.m. back to 1 a.m. And so it's like, so if I schedule a cron job for 1:30, is it going to run twice? And what happens if I schedule it spring forward? If I schedule it for 2:30, when it jumps from 2 to 3, is it going to know that it didn't run the job? Is it going to run it anyway, or is it going to like just be lost forever because it jumped from 2 to 3?
I've always thought it was interesting that we don't end up in some scenario where we just like recurse, where we're just permanently stuck in that hour window where we're going forward and then sliding back an hour. I'm glad people have figured out to do that.
Yeah, like how does the computer know that this is the second time I'm hitting 2 a.m. and not the first time I'm hitting 2 a.m.?
Yeah,
I don't know.
Just want to know that there are two commands in Python for time in its time module. And one is this for system time, another for synchronized time. But they never elaborate what is exactly the difference here, why they both needed. So this is very interesting.
Yeah, I've looked at stuff with the time it module and various other things with Python. There's the Jupyter magic too. And it always returns two values and I'm never confident exactly what is what. And then when you throw into the mix the various multiprocessing things, I really don't know what's going on because it'll say some wall time or something like that. That's like 0.5 seconds, but I just watched it go for 35 seconds or something like that. So I need to learn some more details about that, but I've ran into weird scenarios with that.
I agree with your original comment, Ryan. I had no idea just clocks was such a big deal.
Well, I
wonder
didn't
how
know-
stuff does work.
I was surprised
Ryan.
that it was so hard to keep track of the time, but then I was also kind of surprised to see how reliant so many things are on the correct representation of time. I had never thought that it was that important, because it was always something where it's like, okay, my system, it ends up off by 3 minutes and then it gets resynced, and that doesn't seem like that big of a deal. But when you have a whole bunch of systems that are interacting and all trying to write data about something, that's actually extremely important.
Right. So instead of time, we can use like auto incrementing counters, but then that creates this massive hotspot.
Mm.
Right.
Yeah,
So how do you have a distributed counter, you know?
Look,
That was 2 chapters ago, or last chapter, wasn't it?
if you look up NTP, Network Time Protocol, that's how like global routers synchronize on time.
Mm. Yeah.
So you give you some ideas.
Yeah. So moving on to the next section. So they called it "The Truth is Defined by the Majority." And so they were talking about how in distributed systems, you need to have some way to get agreement, because like we were talking about with the various different leader setups, you might have one node that announces itself as the leader, but then the rest of them say, no, you were unresponsive for the last 5 minutes. We declared a new leader, but then the one still thinks that it's the leader. And so there needs to be some way to form consensus and get everyone to agree on the correct operation. So they talked kind of similarly to the previous section, talking about leases or locks. And so they were talking about that sort of scenario where you end up with a bad leader, essentially, because you have that pause, they check out the lease, and then they end up causing a bad write. And so they were saying that the way that you can defend against this is the fencing token. So what Ted was talking about, you increment some counter and you say, okay, this is leader number 33, and then we elect a new leader number 34. Leader number 33, when he goes to try to do a write, can't actually do the write because we see that there's already a leader 34 assigned. And then it has to go back and figure out the resolution of that. But at least it makes it so that the bad write doesn't occur. Then they talked about the Byzantine faults. So they're saying, what if we don't just have like accidental drift? What if we have someone who is intentionally a bad actor in the network, and they're changing their time, or they're sending bad information, or they're operating without a lease, basically, and trying to do various different things? Can we build a system that is robust to this and can potentially use some consensus in order to make sure that a bad actor or group of bad actors can't essentially start doing negative things on the network? And so they were saying, it's one thing to have a bad actor in the group, but it's also possible for systems to just kind of accidentally lie. So if they get time desynchronized, or they have some system error and start giving bad information to the database, you might want to write something that is Byzantine fault tolerant so that it can handle that potentially. And then in one of the last sections, they started kind of reviewing the different models and the different faults. So we talked about the synchronous system. So that's that kind of closed circuit. We know what the network delay is roughly going to be. We know what the time drift is roughly going to be. We expect it to be very low, but it's pretty inflexible. Then they talked about the partially synchronous. And so that's synchronous for the most part, but then when there's significant traffic, we might end up with network delays, and time drift is possible to occur. And then asynchronous is basically saying we have no timing assumption. Everything can just happen whenever, and the ordering doesn't actually matter. For some things, that's a valid way to look at it, but for a lot of things, you can't necessarily operate like that. Talking about the writes previously, if you just did everything asynchronously, you would just end up with a complete mess, because you might have different versions that are percolating and writing different versions of things over top of each other, and then you don't know what the actual truth is. And then they were talking about the different forms of faults. So they categorized one as crash stop. So you might have an error where you say, okay, this thing failed and it's just offline. It's just dead. We're not going to ever go to it again. And then there's the crash recovery type of fault. And they're saying, okay, maybe it just was slow for a little bit and we can still try to go back to it, and it might still be available later. It's possible that it recovers. But for a period, we decided that it was offline. And then they talk about the Byzantine fault that we just talked about. And it's basically saying that a node can do everything, even trick and deceive. And so you might have to build something that is tolerant to that and say, we need to look across many nodes in order to form an opinion. We can't look at any individual one as the truth. And so their kind of closing note was saying most applications end up lining up as partially synchronous and crash recovery fault tolerant. That's just where most things lined up. There's use cases where you have synchronous requirements, or you might have Byzantine fault requirements, but it's more often that it ends up partially synchronous and crash recovery tolerant. And then right at the end, they said there's a lot of good theory and research, but in the real world, a lot of things become messy. And so even on paper, something might look good, but you have to plan for a lot of different scenarios and say, even when things go wrong, what are we going to do? So that was it for the chapter. Any additional comments, questions?
I'm just puzzled by the idea that node can do intentionally trick and deceive. How exactly it happens?
So Byzantine doesn't necessarily mean that it is a malicious bad actor. It could just be an actor acting badly. I think like the book had some examples of like memory corruption inside the system, that it would still follow the protocols and talk everything, but it was just operating with a bad state of the world. So that falls under that category. But then you also have malicious actors. There are people out there who are trying to subvert systems all across the board. So there can be intention as well.
I guess one example of that, I don't know if this is completely valid, but say you have some distributed system, someone who's an NTP server operator knows that they're using that system, they could change the time knowing that it's going to damage that system, and they get certain nodes that are off on incorrect times, and then all of a sudden that damages a whole bunch of nodes for them.
Yeah, I mean, the reality is almost no systems are built tolerant for Byzantine faults, so it's kind of moot. But the theoretical discussion is that if you look at something like crash stop, crash recovery, so those will look at situations, say, for example, where I sent you a packet and it was packet number 12, and I'm waiting for a response to packet 12. So crash stop says I might get the response or it'll just be silence. And then crash recovery says I might send the packet 12, I might wait, and at some point I'm going to give up. I'm going to time out or whatever. I'm going to give up and say, okay, let's do something else because they're not responding. But then you could, lo and behold, out of the blue, get a response to 12 way later than you were expecting. Byzantine faults includes, like Chris was saying, innocuous things like, what if somehow the server has an error and it responds with an 11 instead of a 12, or a 13 instead of a 12? Like that's not covered under crash stop, crash recovery. And then in the extreme, it's where someone's, yes, purposefully trying to hack into your network. And so then they could engineer packets that have whatever kind of data just to mess you up. Does that make sense?
Yes.
I saw this this paper at the most recent NeurIPS. It was like a month ago, and I don't know how practical it is, but I thought it was kind of interesting because we've seen stuff about like adversarial attacks on AI systems. And so there's been, you know, stuff I've seen, right? Like where you've got the Panda, they add something that looks like white noise, but it's not. It's very, you know, engineered, and it changes the prediction from Panda 99% to like, you know, Gibbon 60%. And so this was talking about other kinds of algorithms. I think it was talking about like count min sketch or something like that. And so there's actually behind the scenes these hashing algorithms. Well, in theory, if you were a malicious actor and you were trying to probe the system, you're trying to crash the system, you could give information that on the surface would look like it's sort of randomly distributed, but it was designed purposefully to like mess up with these algorithms and to cause them to like produce incorrect results. And so they talked about how somebody could probe your system and ultimately determine how your hashing algorithm worked. And so what they did was they actually applied differential privacy to their algorithm. And so they basically had like multiple sketches, and they used differential privacy to show that they mathematically proved that somebody could not probe and ever actually have certainty as to how your hashing was working, and then they couldn't be a bad actor even if they wanted to. So I thought that was kind of cool. Again, it's just theory at this point, but it's kind of cool to see that people have actually thought about how you would defeat an adversarial attack even if somebody had full control of the data they were sending you.
I see, but it's still not node which is tricking. It is people who made it, you know, to do wrong.
Well, I mean, you know, there's denial
Also,
of service
I
attacks,
understand
right?
that there is no difference, you know, when you work with it. Okay.
Right. So like one possible scenario you'd guard against is, you know, denial of service attack. So if somebody got a hold of one node, could they cause the whole system to crash? Like you as the maker of that system might want to have some guarantee that even if a hacker took control of a node, there's no type of messages that it could send that would cause the whole system to crash or, you know, corrupt your entire database.
Yeah.
I think one of the big things about it from the chapter is they go over a lot of different techniques or items to be cognizant of, and it's kind of the exercise of what can go wrong, and then like, you know, going back to the, oh, if I have no response from a backend system, you know, there are 1,000 different ways that it can come up that I get no response from a backend system, but all I really care is, did I get a response or not? And so you kind of lump it into the category of like, okay, I'm going to figure out how to deal with it as to I get a response, I don't get a response, I get a slow response. Like you kind of distill it down into those three kind of core ones, and then you make sure that you build a system that can deal with those three cases. Because a lot of this is about doing complexity reduction such that you can actually deal with a set of problems that you can solve, rather than finding all of the possible ways stuff can break, and then just iterating and improving as new things are discovered and whatnot.
Cool. I think that's it for our book club time.